find it. It's probably at home, right?
It'll probably take me until the next homework is due to find it.
No, you'll find it. Kiddos just joining us, we are quickly going through the answers. I actually already did, but here, we'll do it so that you can see them. Pause if you need to look at them a little bit longer. Number 2, we're checking homework 3, is 2.4 and 2. Number 24 is 0. Number 36 is -1. Number 44 has 4 answers. Pause it if you need it. 3, 3/2, 7, 29, and 9. I gave a little hint to this one. Maybe change 27 to 3 cubed first. The cubes cancel. 3 squared is 9. Anyway. Number 58, multiply by a conjugate, simplify. You get 1/4. Number 62, the answer key made a huge jump unless you use my trick of multiplying by 4 and x plus 4 top bottom. Simplify to be -1/16. Number 64, my hint was x and delta x are 2 very different things. Keep them separate when you FOIL to simplify. You end up, after plugging in 0 for just delta x, to get 2x. Number 80, they did not like because it had an e, but as I showed them, e to the 2x is the same thing as, can I show it on here? Let me try. E, nope, nothing. There we go. E to the 2x, oh dear, is the same thing as e to the x squared. So it really was a difference of squares, and any difference of squares we can simplify using factoring. So then you factor, and then you cancel, and then you plug in, and you end up with e to the 0 is 1, 1 plus 1 is 2, 4 times 2 is 8. Dun, 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 dun. All right, we also had some people do some questions on the board, so if anyone watching this video and not checking needs to see those, you better ask someone in your class for help, because we had people do number 71, 77, 89, and 93, but they're on the whiteboards. All right, kiddos, you are looking at the whiteboards. Any questions you have on what you see? David?
Can you explain 93 like I do with us?
Yes, it's over there. I'll come back to it. Any of the ones up here, 71, 77, or 89?
No, that would be.
Sure.
Yeah, how is that jump in 89 legal? I don't get what's going on.
Ah, you just missed. Does that make sense? Remember yesterday how we can take the limit of one times the limit of the other, so the limit of this is 1, the limit of the other is, plug it in, 0. 1 times 0 is 0. Yeah. Any other questions? Okay, number 93, you need to look at that. Thank you, my volunteers today. You will get participation points. People who didn't volunteer today, no stress, there's another day. Just be ready. Keep working on homework. Ask me questions. That way you can be ready on some of the hard ones.
This one's weird.
93 was a lot like, what was it, 64, yeah?
Yeah.
Except you had to plug in x plus delta x, but plug it in where?
Oh.
So this is f plus delta x, good sir. This is, well, let me write it this way, just to show the difference. This is f plus delta x. Remember, you have to plug in. This is the input, this is the argument, and so you plug it into the x spot wherever it appears in the function. And so 3 times who? 3 times that guy, minus 2, just following the pattern, following the formula for the function.
Oh,
Minus, see it?
Yeah.
Then you distribute, then you combine. Well, here, distribute, boop, boop, boop. There we go. That's why the 2's canceled. The 3x ends up canceling. You see that in the next step. And then you have delta x's that end up canceling, and we end up just with 3. There's not even a need to plug in because the delta x's are gone.
So, that makes sense.
That makes sense. Okay. So what was harder is that you had to set it up. You had your format in 64. They gave it to you already plugged in. I forgot that. Sorry. All right, kiddos. Let's go ahead and get to section 1.4. Continuity.
Oh, shoot.
Saving, exiting, getting into notes. Oh no, we never looked at the piecewise function stuff. Kiddos, on Monday we will do some fun multiple choicey stuff. Yay! But for today, let's write down stuff about piecewise functions, and then let's get into section 1.4.
Is this still 1.4? Oh, yeah.
So 1.3. Remember, this was a slide we didn't, well, I don't think the actual section needed this or put this, but I want to put it because taking a limit of a piecewise function Taking the limit of a piecewise function can be a little tricky. So I'm adding the little addendum to basically sections 1.2 and 1.3. I just think it's kind of helpful to talk about piecewise functions and just take a little bit of notes on it so that you can always reference them if you need to. Or reference it if you need to, I should say. Kiddos, we passed back your summer quizzes and your summer packets yesterday. We kind of forgot some.
Is the summer packet part 2?
Is your Tuesday or Wednesday?
Do they have a video about it? Or
Yeah, it's the same place the other ones were, the limits. It should, oh, you got your summer packet back. It's the same place. Just keep going. Lucy, do you want to? Okay. The piecewise functions, the very final thing from section 1.3. It's kind of 1.2 and 1.3. Let me give you an example of a piecewise function. Let's do triple vision. That's not how it is. For the first case, I say, what if x is not approaching a separator? What if x is not approaching a separator? Who's the separator in the example that I wrote? 0. 0 is the separator in terms of the inequalities as far as the x equals 0 is the boundary from one piece to the other. So if x equals 0 is the boundary, then what's going on when x equals 5? Nothing's stopping it from happening, but even more than that, where is it happening? When x equals 5, what piece is it on or in? Oh, no, because I made this wrong. So what needs to change?
I was confused one of the signs.
I thought I wrote less than or equal to. I apologize. Okay, now it's better. Now it's better. 0 is the separator from one piece to the other, from the left side to the right side. When x is 5, where is it at? The bottom piece or the second piece, and so therefore, in order to find the limit, all I have to do is say, oh sweet, plug it into who? So where's the final answer? Okay, no big deal. If you're approaching anything other than a separator, just try plugging it in the function. If you plug it in the function, you get 0 over 0, keep going, number over 0, it's something infinite, but plug it in the function, whatever piece it's valid in or true in, or works in. But, where does the dilemma lie? If all of a sudden you have, let's use the exact same separator, sorry, the exact same function, however written correctly the first time. You're welcome. Okay. But what if I ask you instead, not the limit as x approaches 5, but if it's approaching a separator, be the limit as x approaches 0. Now what?
You have to plug in
Where?
to both.
Why both? Both sides. And if one side is behaving one way, the other side is behaving the other way, well, who knows if they meet or if they don't meet? So we have to go ahead and check the limit as x approaches 0 from below and the limit as x approaches 0 from above. Who am I plugging it into if I'm coming from below? Yeah, because think of something below 0, negative 0.1. Well, negative 0.1 is less than 0, so it's going to be in the first piece, right? So I'm going to plug in 0 to the first piece. And what's 0 minus 2? So negative 2 is the one-sided limit from below or from the left. You could say the left-handed limit. But as I come from the right, the right-hand limit, or from above, all different ways of saying it. Where am I plugging it into now? The bottom piece. So 1 minus 4 times 0 is going to end up equaling 1. So comparing the two, what's my limit? Because the one-sided limits do not agree. Right? So if I'm approaching, long story short, at the bottom of the page kind of tells you the steps. For if x is approaching a separator in a limit, you have to plug into or think about the limit from below and above. And if the limit below is one function, you have to plug into that function. And if the limit above is another function, you have to plug into that other function, and then you have to compare. If the one-sided limits agree, then the limit exists. And it exists at the value where, or that they both agree upon, right? But if the one-sided limits do not agree, you know the limit does not exist. True? Does that make sense? Every limit you have to come from two sides, so if you're at a separator, well, one side might be one function, the other side might be another function, and then we have to compare. Is that okay? All right, couple more seconds for you to get down whatever you need. We did do an example like this in our workspace of the, 1.2 multiple choice practice in the back of our spirals. So if you want to check out an example, we did one there, but you also had these two examples as well. All right, good, this time, section 1.4. Ooh, that's Tuesday, we don't have school on Monday. P.S. Theoretically, I'm supposed to report for jury duty on Tuesday, so
Wait, you have
we'll see whether or not I'm here.
It's a federal
My
crime
grandma
to
skipped
skip
it,
it,
and
is it
then
not?
she rescheduled it, and she skipped it again.
Yeah, sometimes they don't even go.
Just say
Yeah,
she's
yeah.
an angel. And then they give it.
Miss Dean. My mom has it. She goes, I think she's like in the annual jury. She just got appointed. She has to go like every week.
That is awful.
It's so bad. She just has to walk so much.
Yeah, like your life is just dictated by it.
Just ask what's the case, and when they tell you, say he's guilty, and you should be out of it.
Thanks for all the advice, guys.
Horrible. What if I was in that position?
Bring some poultice and say like you could kill them.
I'm a witness.
No.
We're just trying to help Miss D.
Miss Dean, we should
That's all.
Don't worry, because of you guys, I definitely am trying to not have this last any longer than it needs to last. But at the end of the day, I am not really in charge. So I get to call tomorrow afternoon to see whether or not I actually have to report. I'm kind of praying I don't. But the Lord's will, if I do need to report, then we will just make do. And I'll probably work twice as hard.
For us to, we can watch Donald Duck and Mathland.
Those aren't the videos that we watch.
Oh my
You guys know me, I'll just stay up all night making the videos for the next day.
Okay, we can watch cartoons.
Miss Dean, can I get some water?
Alright, I'm going to zoom in because it's kind of hard to see the four graphs, but each of these four, compare and contrast. Something is similar, but some things are very different. Compare and contrast. What are the similarities? What are the differences? Compare and contrast. What are the similarities? Yeah, but not all. He doesn't, and he doesn't, and he doesn't either. Well, he has a hole, but he has one filled in. He has a hole.
They're all
The
discontinuous.
exactly value of C is undefined.
This one, f of c, is undefined. I agree with that. I'm actually going to write that. That's good. F of c doesn't exist.
But yeah, no, because
Well, let's keep going with the other ones. Does f of c exist here?
yeah.
How about this one? There's a point. Technically, it's a piecewise function, so they made an f of c. How about that one?
Yes, as well.
Okay. So that's kind of well, these three f of c does exist, but the first one f of c does not. All right. What else? What about limits? Let's talk about limits. What's the limit as x approaches c? Does it exist?
Yes.
Yeah. So the function doesn't, but the limit does. Interesting. Okay, I'm going to go ahead and analyze the limits of all the rest of them. How about this one? Does the limit exist?
No.
Function does, but the limit doesn't. How about this one down here?
Sinusoid?
Yeah, we'll just say it equals infinity. How about that? The limit as x approaches c of f of x is positive infinity. We can write it, technically let's say it does not exist, but we can write it. And then the last one, does the limit exist?
Yes.
Huh. Now Tyler, I like what you said a second ago. Let me write this down first before I have you repeat it, as to what they all have in common.
That's a lot of
Where'd you fill it up from?
No, I went in my locker. I should go
That makes more sense.
get
The water pump takes so much longer than that. Okay.
And after the snack track real quick.
Okay, Tyler, what was in common of all four graphs?
They're all discontinued.
Yes. They are all four. They are all discontinuous at? Yes. So my question to you is, what does it take for a function to be discontinuous? If all four are discontinuous, they are all, well, similar and yet different in their conditions. What's something that would make a function discontinuous? Say that nicer.
A hole. Removable discontinuity.
Any form of discontinuities.
Letter A. What made it discontinuous? Don't say whole.
Whole.
Look at what I wrote down. Don't say whole. The function not existing. The function not existing. Yes, there's a hole, but B has a hole, and that's not enough to say no. And C has a, well no, D has a hole, and that's not enough to say no. So, A, that hole made it discontinuous because the function didn't exist. The function doesn't exist. You're going, there's no y. Oh no, I have to jump. You're going as you're following the graph. So if the function doesn't exist, the graph will be discontinuous. Letter B, what made it discontinuous?
One-sided limits don't agree.
What if the function does exist, but the one-sided limits do not agree? The limit does not exist. Is there going to be a break?
Yes.
And if it breaks, is it going to be discontinuous at that break? Yes. So either the function doesn't exist or the limit doesn't exist. What would letter C fit under? The function exists, the limit, well, this is where the technical comes in. Does the limit actually exist and approach a point? So we would say technically the limit doesn't exist. The limit's infinity, it fits into the limit does not exist category. So we'll still say, okay, the limit did not exist on B or C. So either A, the function doesn't exist, B or C, the limit doesn't exist, but D, they both exist. What made it not continuous? The function existed and the limit existed. Huh? Yeah, the one-sided limits do agree, so the limit does exist, that's true, but on D, the very, very last one.
I can understand all of this.
Oh, well, remember, isn't it coming towards the same destination even though it's a whole?
So the function.
So since they agree, they had the same destination, the limit wouldn't be up here. The limit wouldn't be this value that the function is, the limit would be that value. But the limit exists because they're approaching the same
So how
place.
does the function exist? Is it because?
Oh, because of this point. Not because of that, because of that.
F of C or the function is not equal to the limit.
What does it take for a function to not be continuous? Either f of c doesn't exist, or the limit as x approaches c doesn't exist, or they do not correspond. They do not equal each other. Kiddos, look at you. With a little bit of guidance, you just figured out forever card number 4.
Ah, shoot. Wait, 4?
Isn't it 4? 1 and 2, the special transcendental limits is 3. We just covered that one yesterday. Wow.
Oh,
I rolled on
boy.
that one.
The graphs are the
Definition of continuous is 4. What'd you say, Denise?
I said the graphs are different.
Oh, no.
Oh.
Right here.
Oh.
But this is what basically you guys just came to up there, with a little bit of guidance, of course, from you. A function is continuous. Now, wait a minute, this isn't saying discontinuous. This is saying a function is continuous as long as all 3 of these are true. F of c has to be defined. If it's not, it's discontinuous. The limit, hold on. My typing didn't allow me to write the limit as x approaches c. I wasn't doing math type. Hold on, let me fill this in. Ooh, spacing, what's going on? Excuse you. There you go. Oh, that was typing. Okay, so. Make sure you guys get the limit as x approaches c, okay? F of c exists, the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x is the same thing as f of c. The function has a point, the limit exists, and the function's point is the same place the limit says it's approaching as x approaches c. Another way of saying it is the limit. It's not always helpful to think of it this way, but sometimes it will be faster. The limit from below has to equal the limit from above. That means the limit exists, right? And that has to equal the point at. Does that make sense? The limit below has to equal the limit above, so the limit has to exist. That has to equal the point, so the point has to exist, and they have to correspond. So the entire thing is kind of encapsulated in this. Now, once again, this is sometimes helpful to think about, and sometimes it just confuses matters. But sometimes it is helpful to think of a definition of continuity of a function to be that condition being met. If any of the above conditions fail, f has a discontinuity of x equals c. What is the title of this one? Definition of continuous. Not a theorem, it's a definition. Definition of continuous. And why am I going to zoom out and go to a little box and make it yellow? Forever number 4. It's okay, forever number 3 is a short one. We can have a long one after a short one.
I don't even know if I got it down, Miss B.
Really? Is this one with the sine view of v? Or minus cosine view of v? Sorry, go back.
Oh, it's so difficult to hear. Was it, there was just 3 of them.
Was there like
They should make it work. Yeah, that's it.
As long as technically anything you can do, I can do better, but I don't believe that, so I think the other.
Miss B,
Yeah.
does that have to be true for every point on a function, or else it's
For it to
just...
be continuous everywhere. So it works for continuity at one point, but it also works continuity on its whole domain, to be technical. So for tangent, of course it's not continuous at pi over 2, but we know the domain says ignore pi over 2. So tangent is continuous everywhere in its domain. Does that make sense?
Why does this class go by too fast?
Now, is the step function continuous everywhere in its domain? Too fast, David, that's a good thing.
It's horrible. I started like, how much
Oh, you guys didn't get definition?
I
Oh.
needed the last one.
I didn't even...
Note, if any of the above conditions fail, f has a discontinuity there.
Oh.
No, you don't. If any of the what?
Above conditions fail, f has a discontinuity there.
class should be 2 hours long.
What?
This class should be 2 hours long.
I know, right? That would kind of mess up the rest of your classes.
Well, we'll just skip down on the rest of it. It's homeroom, right? It's supposed to be long.
Oh, yeah, a whole extra hour. For those announcements in that Devo.
Yeah, it takes a while.
That's this one.
Just like 10 more minutes.
All right, kiddos, we know this stuff. This is review. Discontinuities. Discontinuities. What if you have something like this? What kind of removable discontinuity is that? That's what you guys are mentioning. Now it's okay to say whole. So removable discontinuity is a whole. Removable means it can be factored out, right? Can be, I'll say reduced out. Because like sine of x over x, we don't really factor that one. We just kind of memorize and say, oh, guess what? Yeah, so simplify. Try to simplify, whether by multiplying by the conjugate, simplifying complex fractions. The nice thing is, we've just talked about all the discontinuities because we faced them in limits. non-removable, well, you guys know the vertical asymptotes. I guess I changed to printing, I felt bad, so you guys would know how to spell these.
Thank you.
Vertical asymptotes. Vertical asymptotes. That's the case then. Even if they agree, it's still a discontinuity. Even if the function agrees at some sort of point, there's still a discontinuity. Now, it could be continuous everywhere but, I'm just making these A's. Everywhere but A. Could be continuous everywhere else, but it's discontinuous at A. There's a vertical asymptote. We could have jumps. Well, actually, let's do breaks. Right, you guys have seen breaks by now with limits and limit graphs. There's all sorts of like broken stuff all over the place. Technically up here we could also have poles and jumps. Jumps I'll define differently. Jumps I'll say are the ones with a hole, but a point somewhere else. That could be a jump. But then there is one other one that would be non-removable, and that would be that funny oscillating one. Like, and I'll do my example again, the sine of 1 over x. Remember that one? Like, what kind of discontinuity is that? Like, we plugged in 0, it didn't work. We're like, I don't know. Okay. Non-removable could also be the oscillating one. All right, you guys got them? Removable can be reduced out. Removable, 0 over 0, keep going. Non-removable, we're stuck. Question, how does the vertical asymptote show up in a function? Remember from yesterday?
Yes.
Number
Number over 0 when you plug in the discontinuity. The 0, it's a 0 of the denominator. When plugged in, gives you a number over 0. How do you see a jump? What kind of function would a break? What kind of function would a break appear in? Piecewise. 2 pieces that don't match up. And then the oscillating one, well, it's something funny, usually to do with trig and a 1 over. Okay, so that's a review on discontinuities. So, we talked about when discontinuities occur. Can you guys tell me some functions that will always be continuous for all real values of x, not just their domain? But they're continuous for all real numbers of x? What type of function always continuous? Constant, it could be a constant function. Sure. So you could say a constant function. And constant function would be like y equals c, right? How about all polynomials? Aren't all polynomials continuous everywhere? There's no square roots, there are no denominators, just a polynomial, 5th degree, 4th degree, 7th degree, 2nd degree. All polynomials. ax squared plus bx plus c, ax cubed plus bx squared plus cx plus d, all of those. All polynomials are continuous everywhere. Isn't e to the x, aren't all exponentials continuous everywhere? Every normal exponential function? Right? Anybody think of anything else? How about like sine, cosine? Those are continuous everywhere, right? They're the 2 trig that don't have any vertical asymptotes. LNs have a restricted, square roots have a restricted, fractions like rational functions, and those denominators, that could be restricted. The other trig could be restricted. I guess you could put like cubed roots, right? Any odd-powered roots? That's not restricted. Or tangent inverse? That's not restricted. That's a random one. He looks like kind of a cute root. Anyway, tangent inverse, he isn't restricted. He keeps on going on forever. Anyways, there are lots of functions that are continuous for all real numbers. There are lots of functions that are continuous for all real numbers. but there are many, many that aren't. We have to keep an eye open. A lot of them we know because their domains are restricted, but then the piecewise functions are the extra ones we have to look out for. Okay, if you have two different functions, if f and g, function f and function g, if they're both continuous, we can say if you multiply a constant times a constant times f, or a constant times g, taking a continuous function and multiplying by a constant, no problems, still continuous. Taking two continuous pieces and adding them together, no problem. The sum will still be continuous, whether you add or subtract. Addition, subtraction of continuous functions will not change their continuity. If you multiply two continuous functions, f times g, multiplication doesn't mess anything up. What will mess something up, possibly? When you divide, everything will be fine as long as what?
G not equal 0.
As long as g doesn't equal 0. Yeah, what does that help with? If I were to ask you for the continuity of the following. Is that continuous? I don't know. Pause, it's okay. Is sine continuous?
Yeah.
Is e to the x continuous?
Yes.
Is e to the x ever equal 0?
No.
Hey, it's continuous. You can just break it down into its pieces. Kiddos, we did not finish this entirely. This homework will be due on Wednesday. But if I were you, try to get a good bit in. Get it started so that next week won't be as hard. We do have a test coming. Look on the calendar. It might have just gotten pushed today, though.
Easy test.
Bye, guys.